All right, ladies, I like to start on time. I don't know where our other participants are, but you're here. So we're going to go ahead and get started. We have a special guest with us today, and let me let her into the room. Where is she? There she is. Hello there. How are you? Oop, hold on. She's connecting. Hi there, Dr. Gregory. How are you?
I'm fine. How are you?
I'm doing fine. I just told our participants, I'm not sure where all the other girls are that registered, but I like to be a good steward of people's time. So I want to go ahead and get started. But ladies, this group of ladies that you see, they participated in cycle 1 and ended in December. So they are ready to go to STEM. They're ready to go and see what we have to offer. They have already gone through the 8-week sessions where we have brought speakers to them. So they've been with us for a while, and they're back. So we're excited today. Ladies, let's welcome Dr. Elizabeth Gregory. She's going to tell you what she does. And because I know I'll mess something up, I'll let her tell you what she does and what we'll be doing today.
Hi, I'm Dr. Elizabeth Gregory. I'm a research engineer at NASA Langley Research Center, which is right here in Hampton, Hampton Roads. We're in Hampton, Virginia on the peninsula. And my research has to do with computer simulations, which we're going to learn a little bit about at the end of the virtual tour today. But the first thing I'm going to start with is a little bit of history of NASA Langley, and then I'm just going to go through the different facilities. And I don't know how you do questions, but I don't know if you type them, but feel free to interrupt me with the questions. I'm happy to answer them as we go along, and I kind of have different things, so I'm not worried about time. We can squeeze things or expand things as we have time. So let me first share my screen. Share. As I said, can you all see my screen? Yes? Oh, perfect. Okay. So NASA Langley Research Center is here in Hampton, and we are, NASA has a couple different kinds of centers. We have space flight centers. So a space flight center builds flight hardware and but also does research. We have space centers like Kennedy and Johnson that mostly are just dedicated to space operations or launching. And then we have research centers, and Langley is a research center. So we, in some ways, we don't have the cool things like mission control or launch vehicles, like we aren't doing rocket launches, but we are doing really critical research. NASA Langley also has the prestige of being the oldest NASA center. We actually are older than NASA, and the first thing that we have is a video. Can you all see the video? Did I just, okay, so I was trying to embed the videos, but I wasn't able to do that with changing from formats. So we will go here, and if someone could give me a thumbs up when you can hear it. No, you can't hear it. Okay, hold on. Oh, geez. Let's see. Sorry about that.
Dr. Gregory, don't forget to share your music, share your sound.
Oh, okay. See, I'm not a Zoom user.
And yep.
Share.
When you
and
share
then
your screen,
share
I think it's,
sound.
yep.
Okay. Thank you very much. Okay.
100 years ago, the National Advisory Committee for Aeronautics, known as NACA, established the first civilian aeronautics laboratory, what is now NASA's Langley Research Center in Hampton, Virginia. From the beginning, Langley engineers pioneered technologies that help all of us travel safer, farther, and faster. Langley's early years focused on solving the fundamental challenges of flight. During World War II, our engineers tested planes like the P-51 Mustang in the nation's first wind tunnel built for full-size aircraft. Changes they made to these aircraft to gain speed and use less fuel helped win the war. As Langley engineers pushed the aeronautics envelope, they partnered with the military on an experimental aircraft that could fly faster than the speed of sound. And in the Bell X-1, Air Force pilot Chuck Yeager flew into history, becoming the first person to break the sound barrier. But that wasn't fast enough. So researchers at Langley went back to the wind tunnels, and by 1959, the X-15 climbed to hypersonic speeds, traveling 5 times faster than the speed of sound, paving the way for spaceflight. As the space race transformed NACA into the National Aeronautics and Space Administration, America's human spaceflight program began at NASA Langley with Project Mercury. Langley tackled the challenges of spaceflight, trained astronauts, and successfully managed Mercury, going on to play major roles in Gemini and Apollo. The moon became the next goal for America. Langley led the Lunar Orbiter program, which not only mapped the moon, but chose where man would leave those first footprints on its surface. And the 12 Apollo astronauts who made those footprints came to NASA Langley to train. Langley engineers also developed the Lunar Orbit Rendezvous concept, an idea that allowed those astronauts to fly to the moon and return safely to Earth. Atmospheric science work began at NASA Langley in the early 1970s. As researchers learned more about the air around us, they improved measurements of Earth's atmosphere, detected dangerous pollutants, and forever changed our understanding of the air we breathe. But planes that flew higher and faster raised concerns about environmental impact. So NASA's science went airborne. By taking instruments to the sky, Langley had a new perspective on our atmosphere. Using what we learned about traveling through Earth's atmosphere, researchers began to figure out how we could land on other planets. NASA Langley led the first successful U.S. mission to the surface of the Red Planet, with the Viking 1 landing in 1976, setting the stage for our journey to Mars. NASA's space shuttle was an essential step on that journey. Langley evaluated shuttle designs, improved materials, and tested landing systems crucial to all 135 shuttle missions. Easier access to space meant more satellites that could be used to observe Earth's atmosphere from above. Learning more about our atmosphere helped us understand the thinning of the ozone layers and its long-term effects. For decades, Langley's instruments and spacecraft have studied air quality, pollution, climate, and the energy from the sun, helping us protect our planet today and in the future. With an eye toward energy conservation, Langley Aeronautics engineers developed winglets, saving billions of dollars in fuel and reducing pollution. In the search for even greener, quieter aircraft, researchers returned to Langley wind tunnels and computer labs to design new planes like those with blended wing bodies. NASA Langley Research Center continues to create firsts in aeronautics, science, and exploration, inspiring future generations to make the next giant leap for humankind.
So that's kind of a nice little overview that I like. I found that video and I really wanted to start there, but it kind of went over the 4 areas that we kind of divide our research up into. And you can see from the video that there are people who are doing really, really different things. Langley has chemists, physicists, geologists, every type of scientist. And then also I'm an engineer. It has aerospace engineers, it has mechanical engineers, it has chemical engineers, it has even civil engineers, electrical, computer science, all of these different types of engineers and scientists working together to solve all these different problems. But we kind of divide it into 4 areas, and I'm going to talk about those areas here. The first one is flight, so aircraft. That means that flying in atmosphere on the Earth. So this is where NASA Langley really started its work. It started as an aircraft research location, so human flight. And one of the ways that it continues to stand out in that way is by having wind tunnels. So wind tunnels are a way to study aircraft without actually having to go and fly the aircraft before the design is complete, because that would be very unsafe. It would also be really, really expensive to build a whole aircraft and then see if it's going to fly well. So we have something called wind tunnels, and wind tunnels create uh, flight conditions in a test section for models of aircraft. And sometimes the models are really tiny. Sometimes they're like, you know, one hundredth, one thousandth of a scale, and sometimes they're quite big. It kind of depends on the type of study that you want to do, but also depends on the type of wind tunnel it is. There are 2 kinds of wind tunnels. The first one is closed, and we call it closed because it is a closed circuit. It has a series of fans that basically push the air around in a circle through. You can see the little test section area right here. This is where you have your little model, and you have your fans, sometimes located, you know, throughout the circuit, sometimes just in one place through the circuit. And one important thing about the wind tunnel is that you want the test section to be smaller than the overall circuit in diameter, because you have a certain amount of air and you're moving that air through this circuit. And then you have a really small area and the air can't slow down to go through that. You have to get the same amount of air that you're getting through a big circuit, like a big cross section, through that little cross section. So that means it has to speed up. And that means the smaller you make the cross section compared to the rest of the circuit, the faster the air is going to move through that, which means it's going to simulate the plane flying faster. The other type of wind tunnel is an open wind tunnel. It's pretty easy to see why it's called open wind tunnel, and that's because you have a large fan that, in this case, is kind of I guess in front of, it's in front of because you think about it that way, but it is pulling the air through the test section. So the air is coming in, you can't see where the air is coming in this side, and it is moving through the test section, and the fan is pulling it in. So the reason that you might have an open test section is if you're doing something like a jet engine that has exhaust, that has stuff actually coming out of it, you don't necessarily want that stuff in a circuit. You just want to create it, pull it through, and then have a way to exhaust it. So now we are going to look at some videos of some of the wind tunnels. We have more than one at NASA Langley. Oops. There we go. Oops, that went through. So this process goes through how it makes these models. So we have a whole place called the model shop, and these are actually, I didn't include these, but some of these people are artists. They're artists and they're technicians that their entire skill set is making these detailed perfect scale replicas of aircraft so that it can be used in these wind tunnels. So sometimes the aircraft, the models are made out of aluminum. Sometimes they're made out of a different material. So you can see that this is a little model of a jet, of a little fighter jet that is being tested in our, I think this is the 14 by 22 that went. So the way that we describe the wind tunnel is we usually say something like the size. So 14 by 22 feet is the size of the test section. That's quite large. Someone was walking around inside it. And then something like subsonic, supersonic, hypersonic, and that tells you how fast the air is moving through it. So subsonic is the slowest, and then supersonic is faster, and then hypersonic is faster than that. Transonic is in there as well. So you can see that this guy here, he's actually got, so right now the air is going slow enough that people can stand in the test section, that they get blown away, but he is blowing smoke. It's just a visible vapor over the model, because sometimes it's hard to see how the air is behaving around the model. Sometimes that's hard to visualize. So they'll, put like smoke in the air, and then you can see it really well. You can see the way that that the flow moves over the different parts of the model. Let's see if we can. They've got a slow-mo video, so you can see how the airflow comes off of the little tip, how it's being spread out that way around the little tip. They have all sorts of instruments that they rig up on the model, where they are taking temperature, they are taking air pressure, they are taking, from air pressure, they can deduce speed, and there's a huge amount of data that comes out of these types of tests. And with the exception of this past year in 2020, because we were limited on what could go on inside, on NASA, these wind tunnels are running almost all the time. Almost every day they are either preparing for a test or running a test or finishing up a test by like moving stuff in and out. These are huge, expensive facilities, and so it's important that we get use out of them whenever we can. It's also really expensive to run them. So this is kind of showing the paint that they've added on there is meant to visualize the flow a little bit. All right, so this is the 16-foot transonic tunnel, and this is kind of there's less happening. But what I did want to show you is that these models behave just like a plane. So when there is air flowing over them, they are providing lift. And what this is showing you right here is how the model is actually lifting up when the air is flying past it. It is just like a plane. It has an airfoil, and so it is lifting up, and it isn't on a flexible like a flexible stand. It's on a very rigid stand. So the amount of lift that is being applied is significant here. And this is basically just analyzing the force that is happening on this joint here. This one is really interesting. I think this one is one of the older ones. It'll say right here. And yeah, flutter. So flutter is when you'll be able to see it here. Flutter, when an airplane moves side to side. I'm getting some connectivity issues, so I may stop my video so I can save on some bandwidth. Okay, so we are going to go a little bit faster. So when it starts moving side to side, it's going to be pretty apparent. You can kind of see it's jiggling a little bit. This is as the wind speed is ramping up, you get the wings are moving a little bit up and down, which is causing some side to side. It's getting a little bit more dramatic. It's like it's flapping its wings a little bit. There. It's even more dramatic. And maybe it doesn't look so dramatic to you, but I want you to imagine that you are on an airplane and your wings start flapping up and down. It would be concerning, right? So this is a problem that they need to solve in the design stage. And the way they do it is by doing wind tests. Let's see, we have, oh, they have some side ones too. There you go. You can see that one pretty well. It's just flapping its little wings. Very scary. Not what you want happening. And the last wind tunnel thing I have is, this is a very, so remember what I said about the smaller the test section, the faster the air is moving. So far we've looked at an 11-foot one. We've looked at a 14-foot one. I think there was a 16-foot one. This one is 11 inches. So people aren't standing in an 11-inch thing. It is very, very tiny. And you can see from the title of this, Melting Models by Aerodynamic Heating. The air is moving so fast, it's causing so much friction that so you can actually see the little air wave, the pressure wave as it's moving past, and this is it melting the actual model. I think this is aluminum, so it is melting aluminum. You can see it's getting very, very hot. And that already that the angles are changing here because, and this is just air. It's just air moving at it very, very quick. So that's it from a different angle. Oh, no. Oh, this is a different model. This is a cone. Someone certainly had a lot of fun with this. They were just like, we're gonna put everything in the wind tunnel and we'll watch it melt today and let's take some video. So a lot of really fun stuff there. Okay. So these are just the different videos I had. Huh. So one of the other things that it showed us in the kind of intro video was things crashing into the ground, crash testing. So after you do the aerodynamic tests, another thing that you want to make sure for any vehicle where people, or even not people, just instrumentation, you want to make sure if that thing is going to come to the ground, that the best possible outcome is going to happen when it comes to the ground. And so that means that we're going to be doing some crash tests. Oh, shoot, that's not what I wanted. Here we go.
4, 3, 2, 1, release.
So that was, oh, I don't want to do it, yes.
4, 3, 2, 1, release.
So we have this thing called the gantry, and it is a big structure. I think we'll see it in some of the other videos where we basically, it's kind of like those giant swings that they have at carnivals, except the swing is a little bit too long and you actually smash into the ground. But it pulls it up on the swing in like a big, parabolic arc. And they have videos looking at it. So this is not a scale model. This is the size. They do this with actual planes. I've got some videos of those coming up. Helicopters. This is a little lander. I don't know if it's an Orion capsule or it's an Apollo simulation capsule, but this is like a little lander that astronauts would come back to Earth from orbit on. And they put sensors inside. Those are crash test dummies, so just like they use on cars. And they take all kinds of data when this happens, and they actually just drop stuff. That's why I was going so fast. Normal. They videotape it from a variety of different angles. Here is a different for an F-28. They have
His elbows don't get large. So if you need to pull them up, to rotate them, pull them up.
They have, I've actually been in one of the aircraft that they get before they've done the crash test, and it's kind of creepy because it's just full of little crash test dummies. They have adult crash test dummies. They also have child crash test dummies, and there it goes, baby crash test dummies. All very creepy. Yeah. But all of this is to make it safer if the worst thing happens. And so they put everybody in there. They put sensors inside, outside. Oh, this is really neat. You can see that they paint the outside. They paint it with little dots. And the reason they paint it with little dots is because then when they take high-speed video, they can track all of those little dots and they can pull it into a computer simulation, and they know the exact velocity of all the different little dots, so they can figure out stresses, forces that are happening on the plane as it's crashing. This all helps them do that because they are tracking all the little dots, and then they have these little patterns that they track too. All of that helps. You can see this kind of a pretty big plane. And there's the wing. I guess that's just artistic, but you can kind of see how big the gantry is. This is not a model. This is a real thing. They're hoisting it up on the little swing set. When these happen, oh, did someone have a question?
Yes, but wouldn't all that work that they did go to waste?
Oh, I'm sorry, I can't hear you very well.
All the work they did go to waste, like it wasn't like.
That's a really good question. That's a really good question. So normally these aren't new aircraft. These are aircraft that have been donated by airlines or by the manufacturers themselves for this purpose. And some of them are older. We're going to look at an older one. So these crafts are usually at the end of their life, but we can still learn something from them. It's kind of like doing some crash test analysis on a car that someone's already driven for a while. You're still collecting some data, but also probably if you are doing a brand new one and you want to make sure it's safe, you might go ahead and build one. You might not put everything in it. So like you can kind of see here, I'll go back. On the inside, they don't have the panels. They don't have the station for the flight attendant to put the things. They don't have a lot of the electronics. So it's not a complete full airplane. They do have the seats because that's important to see how people are going to experience a crash because they are in seats, but they take the stuff that doesn't really matter out of it, or if it's a new plane and they want to crash test it, they don't put it in. So, okay, here we go. Let's look at it again. When we have these crash tests on the center, they advertise them and people come down. Like people, that's what they were. These are all NASA employees. Oh, where'd they go? Where'd they go? These are all NASA employees that are just super excited to see stuff fall down. Sometimes science and engineering is very fun. And they just crash it. And you can see that the wings kind of had an experience there. Then the guy's going around, the wing completely fell off on this one side. Sometimes they crash it more than once. You can kind of see what happened on the inside. They've got these little measurements to see what happened to people's heads. They put people in different positions to see how that affected them, or people. They put the dummies in different. Okay, now, just for fun, we're just gonna watch some more of these. This is a helicopter. They got our little, with the, these types of things are usually so that you can do stuff with video, with high-speed video. They hoist it up. Also, next to the gantry, they just have like a scrap yard, but instead of old cars and old refrigerators, it's different stuff that they've dropped, and it's very interesting. So there we go. Oh. They can put down sand, or they can pull the sand off so they have concrete. They also have, I think this was in the introduction video, but you saw a water crash. So to one side of the gantry, they have a pool, like a little pond, so they can actually simulate crashing into water. Oh, that was, they take video inside, looking at the damage. Okay. Plane flips for safety. So same thing, they cut little dots so they do high speed analysis. This is a small plane, so something that wouldn't have tons of passengers, that would usually just have like a pilot and maybe 1 or 2 passengers. It's a rotor plane. You can see they've put down a lot of sand here. And it flipped over. That's not necessarily what you want to happen with your plane in a crash, for a lot of reasons. You don't want your plane to flip over. So in here, you can see this is inside. They have their own little like flight control, where they have a bunch of different computers and a bunch of different control panels in order to watch and analyze the crashes as they're happening. I think they have, there it is. There's an external camera. Oh, it fell over. So that's kind of one of the more fun facilities that we have. Those are all the videos that I went through. So additionally, we do a lot of research on different types of manufacturing. So manufacturing, building aircraft and spacecraft structures. For this case, I'm going to talk about space and the space and aircraft side kind of in the same way. And one of the ways that we do it, this is actually a robot that I work on. So this is called Isaac, which is the Integrated Structural Assembly of Advanced Composites. Composites are materials that are made up of more than one material, or structures that are made up of more than one material. Specifically, this is using carbon fiber. So you can see all of these little cylinders here have a bunch of little fibers, like you would get on a spool of thread, but they're sticky. And then they all come together, and in the middle, they all come here, and they're laid down as like a single line of tape. This is just showing you, let me give you an example of, okay, this fence right here in the background, this yellow and black fence, that comes up to about your hip. So I'm like 5'5", and when I stand in front of this circular part here, the round part that's standing still now, it's about as tall as I am. It is huge. I think that later on in the thing you'll see how big it is. It's on this big track, and it's laying down material like that. So it lays it down in a little piece of tape, and then it just goes over it, and it makes different structures, and it can make it in whatever shape you can imagine. So this is the new way of manufacturing things. So composites can be stronger than metallics, so stronger than aluminum, but also lighter than aluminum. So remember, when you're dealing with flight, whether it's space flight or atmospheric flight, you have to put fuel in something in order for it to lift off its own weight. So the lighter you can make it, the less fuel you have to put in it, the less energy it takes to make that to either put that object in orbit or to make that object fly. So in aerospace engineering, lighter and stronger is always better. So this is a bunch of, you can see the cylinders really well here. This is a bunch of carbon fiber that is in an epoxy bath. It builds up on different tools. So you can see right here, it's making a cylinder. And let's go back and look at it a little bit more.
Dr. Gregory.
Oh yeah, please,
Go
ahead.
I want to point out in your video, most of the videos that I've seen thus far, I see mostly men. So I want to point
that is true.
Yes, I want to point that out. As the girls have heard previously, the whole reason for this academy is to expose them to STEM, because most of the time you see men.
Yes.
You see men, and I just wanted to point that out. Ladies, you do know that it could be us in these videos, not necessarily all the men. So I tip my hat off.
Actually, that's absolutely true. Actually, the person in charge of the gantry now is a woman. I don't think she was in any of those videos because they were kind of older. And as far as, so now this is kind of an older Isaac video. This was before I came, but they built a clean room around it. So I know that there are some Isaac videos out there where I am in it, but I'm in a full bunny suit. So I have like a mask over my face, and I'm wearing like a hat, like a white hairnet type thing, and I'm in like a lab coat, so you wouldn't be able to tell it was me, but there are those videos out there. However, saying that, I work with women, but I also work with quite a bit of men. There are quite a bit of men, but more and more there are opportunities, and I'm working with more and more women. There are also so the woman who she is the boss of Isaac. There's kind of like a local boss, the person who's like here at the machine all the time, but then that guy's boss is also a woman. Don Jiggly, that's her name. And she is amazingly smart, a wonderful leader, and just one of the best people to work with as far as problem solving. She absolutely has everyone's respect. She's also very tiny. That doesn't mean anything, like it doesn't matter that she's tiny, but I'm always just impressed when she comes in and she just demands everyone's attention, and she's very tiny. And but I work with some outstanding women. I don't know why we don't like being on video that much. But so this is a robot I work on. I take thermal images on this. In the future, I'm going to kind of give a little bit more of an overview about the research I'm doing, but this is the robot that is making those things. The other type of manufacturing we do is manufacturing Oh, shoot, hold on. I think I got these out of, that's okay. Let me go back to my presentation and make sure. Okay, so that was kind of the aircraft side of things. And one of the other things that we do is earth science. So exploring weather patterns, pollution, all of those things. And mostly that stuff is done, that stuff is done with satellites. So this is a video. Sorry, there we go. This is a video of the, no, sorry, there we go.
NASA's Stratospheric Aerosol and Gas Experiment 4, or SAGE-4, is science in a shoebox. The SAGE-4 Pathfinder instrument would allow us to continue the 40-year record of monitoring the Earth's stratosphere at roughly 1/10 of the size and cost of previous SAGE instruments. This tiny but mighty instrument is designed to measure ozone, aerosols, and water vapor as well as, or better than, its predecessors. Aerosols in the stratosphere are small particles that come mostly from volcanic eruptions and large wildfires. Aerosols reflect sunlight, which can affect Earth's climate and can also contribute to destruction of the ozone layer. Stratospheric ozone acts as Earth's sunscreen by blocking harmful ultraviolet radiation from reaching the surface, which helps to protect people from skin cancer, cataracts, and immune system suppression. Since the late 1970s, NASA Langley has developed and matured the technology necessary to measure the vertical distribution of stratospheric aerosols, ozone, and other gases. NASA Langley's expertise in solar occultation, a technique that measures the transmission of sunlight through the Earth's atmosphere as the sun rises or sets, provides immense insight into how to optimize the technique. Unlike its predecessors that looked at only a small portion of the sun, SAGE-4 would image the entire sun, which simplifies the design, improves the overall measurement, and takes advantage of recently developed technologies. The SAGE-4 instrument combines a state-of-the-art telescope with a compact filter wheel and high-performance detector for looking at the sun. Fitting all of this into an advanced shoebox-sized CubeSat architecture enables high-quality science measurements in an efficient and affordable package. The SAGE-4 Pathfinder prototype and all of its components have undergone months of rigorous testing at NASA Langley. The SAGE-4 Pathfinder, with a 1-year on-orbit projected lifespan, can demonstrate the potential for a SAGE-4 constellation with a projected multi-year lifespan. SAGE-4 enables a sustainable way to monitor the health of Earth's ozone layer, our atmospheric protection for life in water and on land.
So that is one of the satellites that Langley was not only helped design and build, but also collects data from, or sorry, if there is a SAGE-3 that is up there right now that they're currently collecting data from. SAGE-4, I do not believe has launched yet since this is since this is just back in November, and it will be coming. So it's replacing a SAGE-3. And we have scientists that get that data and analyze that data. I want to make sure that there is time for questions, so I'm going to skip ahead. We also worked on designing and building. This is a method for building spacecraft in space. So it's talking about how expensive it is to launch things into space, and wouldn't it just be better to be able to build them in space? And so it's describing all the ways that we help design specifically this arm that is going to be added to the space station that can be used to add more structure to the space station. Big flexible arm right there. That's a good thing for it. And then here is them testing it at NASA Langley. There it is. Move it around. And remember, this works in 0G, so they have to kind of give it some help. It's on the little wheels and things, and they're analyzing how it's moving. But I did want to make sure, speaking of women, I'm in this with our newest, is it still the newest facility? It might not be the newest facility, but it is very new and very exciting, and one that I am very thankful for because I do a lot of data analysis and computer work. And it is the Katherine G. Johnson Computational Research Facility. I think this is a really good video. It talks a little bit about Katherine Johnson. For people who don't know, Katherine Johnson was a mathematician called a human computer during during the Mercury, Gemini, and Apollo era, where we were trying to figure out how to launch to the moon. She was doing calculations for launch trajectories before we had computers, before when all the computers that existed took up a huge amount of space and couldn't do that much math. They had human beings doing that math. And kind of because of just because of skills that they had that women were encouraged to acquire professionally, most of those human computers were women, and they turned into the first computer scientists. So it goes into little bits on the in the video. But if you didn't know, if you've never heard of the movie Hidden Figures, Katherine G. Johnson is the main character, and then they also include some other African-American women mathematicians, scientists, and engineers in that story. They fictionalize it a little bit to put them all together at the same time, but it's an excellent movie, and it talks about really what these men had to overcome in order to do this outstanding work that they did. And Katherine Johnson was at NASA Langley. She was a human computer here, and they named this facility after her. So here is the video.
Hi, I'm Vince Whitfield, and we're here at the Katherine Johnson Computational Research Facility at NASA's Langley Research Center. We're about to cut the ribbon on this state-of-the-art facility, but before we do, let's take a sneak peek inside the building that will enable innovative research and development across all of NASA's mission areas. Let's take a look inside. This building, the third new structure built in the last 6 years as part of the center's revitalization plan, is named for Katherine G. Johnson. For those watching who may not know, Ms. Johnson is a human computer, an amazing mathematician who calculated trajectories and played a key role in America's human spaceflight program, including the Apollo 11 moon landing. Featured in the lobby is a beautiful portrait of Ms. Johnson that was taken last year at nearby Fort Monroe by famous photographer Annie Leibovitz for a Vanity Fair magazine article. We also have items here that recognize Katherine and the other human computers, like an official proclamation from the Commonwealth of Virginia and a Group Achievement Award from the NASA Administrator. A little less than half of the space in this 37,000 square foot facility is dedicated to supporting the employees of the Office of the Chief Information Officer and those who will be contributing to and benefiting from the technologies that are housed here. Researchers from across the center will conduct a variety of computing projects here, including aerodynamic modeling, entry, descent and landing calculations, and computational fluid dynamics. The facility advances Langley's capabilities in modeling and simulation, big data, and analysis. Much of the wind tunnels will one day be handled by powerful computers, such as those in the CRF. Now, let's go take a look at the guts of this high-tech facility. The data hall has a maximum capacity of nearly 200 racks. That's enough to store almost 4,000 systems here. You may have noticed the racks are mostly empty right now. About 1,200 servers will be moved from their current locations on center later this fall, allowing us to consolidate numerous server rooms and data centers from across Langley into this one data center here in the CRF. When all of the systems are moved, there will be about 13 miles of copper network cabling and 97 miles of fiber optic cable in the building. Now I know it's loud in these rooms, and here's why. The electrical power plant that powers the IT functions of this building can supply 2.1 megawatts. That's enough to power a small town. Because of the importance of the information on the servers, the building is designed to withstand Category 3 hurricane conditions. There are generators that can run continuously even in the event of a power outage. And it's on track to receive LEED Silver certification from the US Green Building Council. The building is an energy saver, 33% more efficient than energy standards just a few years ago. So that concludes our quick look at this new building, a building whose capabilities and people will help to address NASA's future challenges. Speaking of the future, we have a special treat from the next generation of NASA employees from our Child Development Center here at NASA Langley.
So Katherine Johnson actually passed away earlier this year, but she was there to celebrate NASA Langley's 100th anniversary back in 2017. She was there for a couple panels after Hidden Figures came out. I think that same year, I think it was 2017. She sat on panels. She really is an inspiration to all of us. I think it's really, so those servers have been moved over. I've been in that room. It is both cold because they have tons of air conditioners going and very, very loud. But that houses our center cluster, computer cluster, which I use a lot for my data analysis, called K. I don't know why it's called the K cluster. I've heard a couple different stories, but no one knows what the truth is. But it's a very powerful collection of computers that people use. That took a little bit longer than I was hoping, but we do have a couple minutes. If anyone has any questions, I'd be happy to share them. Go ahead and stop sharing, and then.
Dr. Gregory, I would like to ask, how did you choose to go into this field? Did you always know when you were a kid, did you always know this is what you wanted to do?
I didn't know that this was exactly, that what I'm doing now was exactly what I wanted to do, but I knew that I enjoyed math and science. And so I knew I wanted to be some type of scientist. I didn't know what an engineer was until I got a little bit older, until like middle school and high school. And then I knew that I wanted to do engineering. And I started out in aerospace engineering because I thought space was really, really cool. And I've kind of gone around and I've done different stuff with engineering, and I've done structural mechanical things. I've done satellite things, and where I kind of settled was just because I found wonderful people to work with who gave me opportunities to do exciting stuff. But I know people who came at it from very different places too, who weren't thinking they were going to be engineers, or weren't thinking you're going to do NASA and aircraft stuff, and maybe went into chemistry and then found their way here. So I work with people who knew this is what they wanted to do from when they were really young, and people who were like, oh, I thought I was going to be doing something else, and came to it. So those are both perfectly fine paths to come at from. So yeah.
What skills would you say, so as a middle school or high schooler, what skills would you say you would need to, like, not perfect, but to develop in order to go into a field such as this?
I would say that the most important thing is curiosity. So wanting to kind of figure things out makes you a good scientist and an engineer. And there's all these things that just are helpful in life, being self-motivated, teaching yourself something that you didn't know. I really, looking back, I wish that I had more of a self-motivated learner before really grad school is when I figured out how to teach myself things. And so that's really wonderful. But I think that curiosity leads into all of those things. I could say things like being a good writer. That's always good. Being careful with your work and checking your work. That's really good things too. But if you don't have the underlying curiosity, then all of those other things they're good, they're helpful, they're going to help you succeed in whatever you do, but the curiosity is going to fuel you through frustration. And I don't think that people say this enough, but science and engineering, a huge amount of it is frustration. A huge amount of it is stuff not going right, and then it goes right once. So dealing with that frustration and being curious enough to stick through that frustration is always going to help you through.
Great. That's great information. And no, you don't hear people say that.
Yeah, it's a lot of they advertise those crashes that people want to go see, and I can't tell you how many times they'll advertise them and then they'll send out an email and be like, oh, we have to postpone, something's not working. And so yeah, it's a lot of frustration until it finally works.
Gotcha. We appreciate that. We are so happy that you are sharing with us today. Thank you so very much.
Thank you so much for having me.
Absolutely. Girls, we are at our time limit. I hope that you will join us next week. We will go to Oak Ridge Laboratory, which is in Tennessee. So I hope that you have a STEM-tastic week, and we will see you next week, same place. Make sure you keep your same Zoom link, because that same Zoom link is used for every session, okay? And actually, I'm wrong. It is, hold on. I feel like I'm wrong. It's not next week. My next one for this virtual tour is, I am right, the 23rd, yes. Had to look at that. For some reason, I second guessed myself there. But yes, next week we will see you again for our STEM Academy, the second cycle, our virtual tours. All right. Thank you. Bye-bye. Leah, you still here? Oh, she hung up. Okay. All right, Kyla, what'd you think?
I thought it was interesting. I was a bit disappointed that it was only videos. So there wasn't a whole lot of information. And I felt like some of the things like she talked about, it kind of just went over the girl's head because she didn't take a moment to explain it. And I was like, I understood because I had learned it in class, some of those things in class already. But then I didn't know how to ask her a question so everybody would understand.
Right. And it's funny, you know, when you have presenters and you tell them exactly what you want, and when they're presenting, you just kind of have to play it by ear, whether to stop them or, you know, because I mean, you know how it is presenting, you kind of a one-track mind, you know. So I think though, and interesting you said what you said, who was supposed to be here was supposed to be here. So the two individuals, Leah and Jalay, they were, they participated before, and they are well beyond their years, definitely. So I am 100% certain they got it. The other, so there were a total of 13 girls who participated, and two of them actually were on the first one, the first call at 11. They should have been on this call. So they may just have been, you know, confused. I'll give them a call later. But, you know, I'm always not nervous, but just, well, yeah, maybe nervous. Because when you do things like this, you want people to come back. And that very first session, I think is always the most important, because that will determine whether they return and whether they tell people, hey, come join this. So the good thing about today, the two who participated, they know what to expect with the academy. So I think they will return. The other young lady who participated, I can't remember her name, she actually,
Charlotte?
yeah, Charlotte, she participated in the first one today for the first time. So do I tell her she can't participate? Absolutely not. Nope. If she's interested and she wants to return, you know, yeah, I really want to just expose them. Yeah, you're supposed to follow by the guidelines and all that good stuff. But if she wants to come to the second one too, oh well, that's good. Well, good. Well, I will not hold you anymore for your Saturday. I hope you do something fun before your semester gets started and the fun goes away. So- and I haven't had breakfast yet, so I'll get something to eat.
Oh, please go eat.
I know. Well, I just could not get myself up. I got myself up at the very last minute to come downstairs and get ready. I don't know. I think Saturdays, I say this all the time, Monday through Friday, I usually don't have I'm up at 6 o'clock every day. But something about Saturday and Sunday, it's psychological. I'm not supposed to get up at 6 o'clock. So I had difficulties getting up this morning. So I will go have some lunch now. And I will talk to you next week.
Yes.
All right. Sounds good. Talk soon.
Thank you.
Bye-bye.
Bye.